Welcome to The Explainer. This is where we break down big topics into clear, easy-to-understand insights.
That's not just some deep philosophical question. When you get into the world of machine learning, it's actually a proven winning strategy.
Yeah, it's the core idea behind one of the most powerful techniques in all of artificial intelligence. And you can think of it like this. Instead of trying to build one single, perfect, super complex machine to solve a problem, this technique lets us build these incredibly accurate models by combining a bunch of simpler ones. It's all about the power of the collective.
So, what is this magical technique? Well, it's called ensemble learning. And honestly, the best way to understand it is to think of it like a quest to build the perfect team of predictors. Okay, so our first strategy for building this perfect team is called bagging. And it works a lot like a democratic vote. The name, by the way, is short for bootstrap aggregating. So, how does bagging actually work? Well, imagine you've got this huge pile of data, right? What bagging does is it creates a bunch of different random subsets of that data. It's kind of like giving slightly different textbooks to each member of your team. So each model trains on its own, completely independently. And then, when it's time to make a prediction, they all get an equal vote. And that diversity is absolutely crucial. It's what makes the final decision way more stable and reliable. In the world of machine learning, we call this reducing variance, and it's a fantastic way to stop a model from overfitting, where it just memorizes the training data instead of actually learning. And probably the most famous example of this is the random forest algorithm. Seriously, random forests are an absolute powerhouse in machine learning. And they do exactly this. They apply the bagging technique to a whole bunch of individual decision trees. That's why it's called a forest. And that forest is way, way more powerful than any single tree could ever be. Okay, so that's bagging. Everyone works in parallel. But what if we tried a different approach? What if our team actually learned from each other's mistakes? Well, that's the big idea behind our next strategy, boosting.
Boosting completely flips the script. Instead of training independently, the models learn one after another in sequence. It's like a mentorship program. The first model, our weak learner, makes a prediction. Then we look at all the mistakes it made. In data science, we call these residuals. The entire job of the next model is to train on those specific errors. Then the third model comes in and learns from the second model's mistakes, and so on and so on. Each new member of the team is laser-focused on the toughest problems, which makes the whole team get smarter and smarter with each step.
A great example of this is a popular algorithm called AdaBoost, which stands for adaptive boosting. What it does is it gives more weight, or more importance, to the data points that the previous model got wrong. It's basically like telling the next team member, hey, the last person really struggled with these specific problems, so I need you to focus all your energy on them. And it's this relentless focus on fixing mistakes that allows boosting to reduce a model's fundamental inaccuracy, what we call its bias.
So let's just nail this down, because it's really important. Bagging and boosting are two fundamentally different ways to build your team. Bagging, our democratic team, is all about working in parallel and being independent. Its main goal is stability, reducing that variance we talked about. Boosting, the mentorship team, is sequential and dependent. It's all about one model learning from the last, and its main goal is raw accuracy, reducing bias. All right, so now let's talk about supercharging our team. Let's get into a more advanced form of boosting that has pretty much come to dominate the entire field. So gradient boosting takes that mentorship idea and refines it with some really powerful math. It uses a technique called gradient descent to hunt down errors. The best way to picture it is to imagine the model's error as a giant valley. Gradient descent is a clever way of taking these very careful, calculated steps downhill to find the absolute lowest point of that valley, the point of minimum error. It's an incredibly precise way to correct mistakes. The only catch, because it's so careful, it can be pretty slow to train. But what if you could get all that incredible power, but make it, say, 10 times faster? Well, this is where the story gets really, really exciting. An algorithm came along that did exactly that, and it completely changed the game. I'd like you to meet XGBoost. That stands for Extreme Gradient Boosting. People often call it gradient boosting on steroids, and for good reason. It takes all the mathematical genius of gradient boosting and just turbocharges it with some brilliant, brilliant engineering. It was built from the ground up for one thing, performance. So what makes XGBoost so extreme? Well, it has a few superpowers. First, it's a master of parallelization. Even though boosting is a sequential process, XGBoost is engineered to do a ton of calculations within each step at the same time. Second, it's optimized for your hardware, making the absolute best use of your computer. Third, it has this amazing thing called out-of-core computing, which means it can process massive data sets that don't even fit into memory. And fourth, it intelligently handles missing values, which, trust me, saves data scientists a ton of time. It's this mix of raw power and smart design that makes it such a champion. And you don't have to take my word for it. Just look at the stats. For years, XGBoost has absolutely dominated machine learning competitions on sites like Kaggle, which is kind of like the Olympics for data scientists. In 2015, out of 29 winning solutions published, 17 of them used XGBoost. This isn't just theory. This is real-world, state-of-the-art performance. Okay, so far, the teams we've built, whether with bagging or boosting, have mostly been made of similar kinds of players, like a team of all decision trees. But what if we built an all-star team, a team of different specialists? Well, that brings us to our final strategy, stack. Yeah, instead of a team of similar players, stacking is all about building that all-star team. It's also known as stacked generalization, and the whole idea is to combine completely different types of models. So you might have a decision tree, a linear regression model, and maybe a support vector machine all on the same team, working together. So how does that work? Well, it's basically a two-step process. In the first step, all your specialist models, the base models, make their own predictions. Then you have a final model, called a meta model, that acts like the team manager. Its job is to look at all the predictions from the specialists and learn how to best combine them to make the final call. It's literally learning when to trust one specialist over another. Okay, wow. So we've covered a lot. We've got bagging, boosting, XGBoost, and stacking. These are all incredibly powerful strategies. But the big question is, how do you choose the right champion for the job? Let's break it down with a quick cheat sheet. If your model is too complex and it's overfitting, meaning it has high variance, your best bet is bagging. It'll help stabilize it. Now, if your model is too simple and just not accurate enough, meaning it has high bias, then you want to use boosting to improve that accuracy. If you need top-of-the-line accuracy and you're dealing with a huge data set where performance is key, then you go with the champion, XGBoost. And finally, if you're trying to squeeze out every single last drop of performance, maybe in a competition, stacking can give you that final winning edge. So, what does this all mean in the grand scheme of things? Well, Ensemble learning really shows us something profound. As these AI models get more and more complex, maybe the future isn't about building a single lone genius model. Maybe it's about getting better at building and orchestrating incredible teams of models. What you should really take away from this is that collaboration is absolutely key, even for algorithms. The whole really can be so much greater than the sum of its parts.